column designs or the preliminary design for columns. This procedure we'll be learning today is a general procedure for column behavior. Next year, when we start talking about, in particular, we start talking about steel columns and concrete columns, we will learn how to analyze and design those. But that procedure we will learn next semester will be based on the understanding what we learn here. What will happen for a column acting under axial load? We always talk about axial load. Just to remind you, the load applied to the section. If I have a column here, vertical column, if I have the forces applied axially, that means always the load is either pushing down or pushing up, depends on the direction of the force. If the force was a tension force like the green one here, pushing up, that means this won't be considered, it's not acting as a column, will be as a tension member, okay? But when it's axial compression force, that's where we consider this member as a column. So in theory, just so you know, guys, a column is not necessarily to be always vertical. If I show you some examples from design, go to structure analysis, Revit files, column buckling. Let's look into that to start with. And most of you, I think not next semester, the semester after, you guys will be doing structural analysis, structural drafting too, which is we start doing the designs for this type of structures. I think Ina is doing the subject currently, so she will know this structure as a steel warehouse. Okay, so obviously you can tell this if this is a steel warehouse, guys, so you understand what this structure is. Okay, just a large warehouse made of steel frame. Okay, these are the main components, I would say, before we start adding purlins and girts, which is for, when I'm saying purlin and girts are other components, you will learn them later on. They'll be supporting the sheets on the outside. The sheets on the outside is the finished material, and we call them cladding. So before, that's the main structure of the house, of the warehouse, and these are the main components are resisting all these forces. So you can tell, obviously, this member here is a column supporting the weight of the roof and the weight of all these components here at the top. But also, this member here would be acting as a column. So always, it's not necessarily for the column to be vertical. These members here, look at them, they're separating these two major frames. So if I look at this frame here, we call it portal frame. Together, that structure, we'll call it frame. So I've got 1, 2, 3, 4, 5, 6, 7 frames altogether. So if I have these two frames here next to each other, or these two frames, these members are separating these two frames, keeping them at certain distance. And mainly these members between them acting as columns. They're always under compressive forces because these frames that try to move to the side, moving this way or that way, and this member here will push back to keep it in place and supported on this frame here. So these will act as a columns, what we call them struts. So you'd be familiar with those, called strut. Okay, so but in terms of behavior, they will all behave as columns or a member under compressive forces mainly. The forces are applied there are compression forces, so there's no tension forces here. That will be compression forces mainly. And these, for example, rods here, the steel rods, the bracing rods, those will be under tension forces, and we consider those as bracing members, okay, under tension forces. That's just a general view on what you may be learning for the coming semester. So all of these knowledge will come together. Okay, so we'll keep this in here. Let me just have a quick look at another file I've got here. Columns, see what files I've got there. That's just the connection between them. Yep. Okay, we'll keep that one too. All right, let's go back to our lecture. See how we'll tie all of this together. So, the one formula, the same as when we've done for the beams, the one formula we'll be dealing with today, it's called Euler's equation for buckling. Euler's equation, this one here, okay? That will determine the buckling or critical load, what we call it. We'll understand by the time we get to the end of this lecture, we'll understand what is buckling and what is Euler's equation, what does it take into account for the buckling load. To be able to do that, we will have to look into the expression of effective length rather than actual length. Everything we'll be talking about now, for example, for the beam, we're just talking about L, the length of the beam, or sometimes we call it S, the span of the beam. But realistically, or accurately, even if we look at a beam, if I have a beam between two components here, let's say I've got this beam here. This is L from this point to that point. That's the length of the beam. This is L, but there's a new concept we will learn called LE. We're not going to do it for beams. That will be next semester again, called the effective length. But similarly, today we'll learn for this column here, that's the overall L of the column. But there is another concept we may, based on the conditions, we may get to a point, this is LE, way shorter than the actual column, or could be sometimes LE longer than the actual column. LE could be longer than the actual column. The effective length, we call it. So we'll come across this concept here. Let's just close that for now. And just get rid of this. And also we're going to talk about the slenderness ratio of a column. Slenderness ratio of a column, very important concept that will determine the effectiveness of this column in theory. It talks about the geometry, overall geometry of the column. Okay, these are the points. As soon as we calculate these small variables, everything else is exactly the same what we know, and that will allow us to calculate using Euler's equation, what we call it the critical buckling loads. Okay, now in terms of buckling, if I will have a ruler, steel, I'm using the steel ruler, guys, example, or almost in many occasions, because very ideal to what we need to understand about a member, that the width is way smaller compared to the depth of that member. So it's thin, in this direction is thin, and deep in that direction. So if I have this ruler here, sorry, go back to it. Let's draw it properly this time. if I have this steel ruler here and I applied compressive forces on top of this ruler, I pushed down on this ruler. We discussed that earlier during this second term. What will happen to this ruler, guys? Can anyone tell me? What would you reckon if I push down on the ruler?
Will bend in the middle.
When you say bend, you're referring to
Flexion, like
okay.
the shape will change, it will become a curve.
Okay, perfect. So what Saverio is suggesting that will happen if we push on the ruler, okay? So that's not bending. That's not called bending. So bending, that is not bending. Okay. The second scenario I may ask, would it any chance that this will crush in a way that if I would just draw it that way, any chance with this circumstance here for this ruler, by any chance I'll be able to achieve that somehow? Like I'll be able to just, without buckling to the outside, it will just do that, just crash. Is there a chance for that to happen? In other words, can I compress it without it buckling to the outside? I'll give you an example of that. Any chance I can get to that point for the ruler? I can compress it that way. Have you ever seen, if you push hard on a ruler, that will do this? What do you think? Yes?
No,
You reckon there's a chance? Anyone said yes? Okay. So this is not a realistic scenario. That's not going to happen, especially with this geometry of the ruler. Why I'm certain about this? Because I know this is a slender member. So from here, from this concept here, slenderness ratio, keep an eye on that word. This is a slender member. So I can say here, slender member. What does it mean, slender member? We discussed that before too. It's very long comparing to its thickness. It's not very stable in a geometry way. So if I push down on it, the member will find it easy to buckle away rather than bending, Saverio, what we call this buckling. Rather than bending. Why? Because bending will happen if you have, if I am trying to bend here and there, applying moment, that would bend. Buckling, it's unexpected response when I'm pushing down. If I am pushing down, I'm expecting this ruler to move down without going to the side. But if I am trying to bend it to the side, that's expected. That will be bending. So bending usually happens for beams. When you have a beam like this, and I'm pushing from the side here, that would bend the beam. But if I have this beam here, and let's say I've got roller support here, and I'm pushing from here, and this to do that, that's called buckling. This case is bending, this is buckling. Okay, they're slightly different things. I'll give you an example of that. If I look at this beam here, this is the original. If I'm assuming this is a beam here supported on two sides on columns, can you see this beam here, guys? Let's assume assuming that I've got a column here, column there. This, what you see here is the plane. It's just imaginary plane where the beam is sitting in, okay? So if I'm pushing from the top here on the beam, and the beam will deflect the beam will deflect that way. Look at it. You stay within its plane, but just deflected to the downward. Deflected down, that's bending. But for any reason, if I push at the top, and this may happen a lot, and for some reason, the beam would buckle to the side. Look at it here. Outside the plane, we call it buckling. So I start with, do we understand the difference between bending and buckling? All good, guys? Anyone is not clear on that? So if I am bending, if I'm pushing on the beam from the side, applying forces on the beam from the side, and that beam is bending down like this here, that's called bending. Normal. We are expecting this, I'm pushing on it down, and that will bend. But sometimes if you push on it down, that will for some reason go to the side, will try to escape the load to the side, and that's called buckling. Okay. The same thing applies for columns now. So columns, if you are pushing on the column down, you expect this column at least to compress down to get to that point here. To get to that point there. That's what you expect should happen. But in the case, if I have this column to be, look at this sample here, it's short and wide. If I had the opposite scenario, I having long, thin column, this column will find it easier just to buckle rather than compressing down. Anna is asking if the force is Fy is bending, Fx is buckling. So in theory it is, Anna, but when we talk about beams later on, you'll find, I'll give you some examples. Let me just go give you some photos, realistic photos that you can see. Notes, beam deflection. Let me give you this example, Anna. Look at this ruler here. Let's try to analyze this ruler with weight at the end. Okay, let's try to draw it. It's just a ruler made of plastic, and I've got loads at the end acting down. So I can draw it in a way like this. A beam fixed where I'm holding it with my hand at the back, and cantilever at the front. Okay, and I've got load applied here, B. So you do expect this ruler simply just to, what it does, if I'm looking here, I'm looking at it from the side. If I'm looking at this ruler here, if I'm standing here and looking at it from the side, so why can't start that? If I'm standing here and looking at it from the side here, what I'll be seeing, this is the ruler, this is the load acting down, and what I'm expecting to see that the ruler should deflect. The ruler should deflect that way. But instead, what we see here, from the top, if I'm standing here at the top and looking down, what I see instead from the top, the ruler, rather than going straight, for some reason just goes to the side. Look at it. The ruler, rather than being straight like this, just going to the side. And that's called buckling. So it's not always, although the load I applied here, it's from Y direction, not X. So you would expect this beam to bend only, like what we agreed on here. But although I applied the force from the top down, the ruler buckled to the side. Make sense, Anna? So in theory, all what you need to know, when do we know it's buckling, when do we know it's bending, rather than thinking about it, Anna, if the force applied from X or Y, think about it this way. If a beam bending in plane, this is the plane of the beam. Look at it. This is the plane here. If the beam will bend in plane, doesn't go outside this plane, that's bending. This is the case here. If a beam bending out of plane, that's called buckling. Look at the plane. This is the plane here, and the beam is buckling to the outside of that plane. Anna, do you have a microphone? If you don't mind, can you just explain to me what does it mean by does it depend on the perspective?
No, I'm not sure if I understand or not. If you could give me more example.
Yeah, of course. Of course. Thanks for your question, Anna. Okay, guys, think about it this way. Let's go back to these two examples. Let's go back to this example. Let's focus first on columns to start with, okay? Let's forget about beams for a minute. Let's go to columns. Do you remember the example that I gave you maybe at the first lecture? If I have a can of Coke, just get a can of Coke, just that after you finish drinking it, obviously. If you push down, if you stand on that can of Coke, if you push down, what will happen? The can of Coke will do that. Simply will just crush. This is the face and this is the bottom face here. And all of that between the can here will crush. If you apply large force on that can of Coke, okay, it will be crushed. Why? Because the can of Coke is very stable. It's wide. Look at the width here. It's wide and short. So if I say H on B, let's call it that way, the height on the width is a small ratio, not very high. So let's call it H on B. It's small ratio. So the height is not very much higher than the width of the item or the member. That is failure. That is yielding, what we call it crushing. In fact, what we call it for columns. Buckling, Anna, will come in a slightly different way. If I have long member and thin, these type of members, we call them slender members, rather than stocky. Here, we call it stocky member, the opposite, like a stocky person or slender person, okay? So the word slender, that means it's tall or long, very thin at the same time. So we have to learn this concept. It's something new to you guys. You never thought about what is slender member, what is not. We talked about this in trusses. Trusses are made of slender members mainly because we don't want these members to be very thick. We just mainly work on axial tension and compression for trusses. But regardless of trusses, if I have a column, if I have the column to be very long and thin, we'll consider this member to be slender member. If I have the column to be short and wide, that is stocky column, we call it. In this case, if I push down, the column will find it easier, the ruler. If you just take this ruler here, Anna, so this exact ruler, that why I can't see the mouse. That's why. So if I take this ruler here, take exactly the same ruler and try to use it as a column, what we have it here, and push down, the ruler will bend, or sorry, will buckle to the outside. We will discuss bending and buckling and differences between them further next semester when we talk about beams. All right, guys, so that we have a whole lecture there, just trying to understand what does it mean for a beam to buckle, what will happen. All of those, we discuss the radius duration again, which is we are discussing today, and we go through it for the actual design. But mainly for a starting point for what we need, and hopefully that will be next semester, will be face-to-face. I'll show you those in the class. We've got some design aid there that we can show you those exact phenomena of buckling and bending and the rest of them. But for a column, are we okay with these two difference between these two cases to start with, guys? Anyone having problems with these two cases? I can see Anna saying it makes sense, but anyone else? Anyone finding it hard to visualize the difference between a can of Coke and a ruler under compression? They completely do two different behaviors, okay? So the can of Coke will represent what we call them short columns, and the ruler will represent long columns. So long columns, if you look at this one here, we'll find an easier way to escape from the load by buckling away. Short columns, now they can't escape the load, they can't buckle to the side, they'll try to resist the load until they crush and completely fail. Okay? So, based on that understanding, we can classify our columns into mainly three different scenarios. These scenarios are short columns. They will fail by compressive yielding, or what we call squashing or crushing of the steel. And long columns where the cross section of the column is small compared to the length of the column. So please think about it. If I would ask you a very quick question, can you see this exact column here? This column is failing under buckling because we are assuming this is a long column. If I will use exactly the same column, but I'll take a small piece of it here. So if I would just simply, you see, second. Should be able to. There we go. Okay. If I will take a small piece of that column, just like that here. So the column, rather than being that long, I'll look at this as a column. That will be the height of the column, and obviously that's the width of the column. And I push on it. So that's the new one, the new column. And if I'll put the same weight, wherever that weight is, on this column, short column, this column, would it do the same as this long column at all, guys? Would it buckle away like this? Shouldn't, correct? So that what will happen, this will simply, again, go back to the Coke, can of Coke situation. That will squash. It'll be just like that. Will be squashed. That's what will happen to it. And also, I'll take another example. So if you might think, well, the length then is the problem. So just if I change the length, that stops buckling. What about if I take the same length of the column, same length like this, but instead of using just that width, if I make that column very large here at the bottom, just something like that. Do you reckon this column now will fail the same as that? So I will not, if I make it a large column like this here, again, that will not fail anymore in buckling, will fail under squashing, which is this one, the yield failure. So based on what we discussed here, guys, perfect. Thank you guys for the guys that are sending comments. So if you look at what the two cases we looked at, so from here we found, well, it could be the length is the issue. By shortening the length, it's not buckling. But then we looked at it, even if I keep the same length, but made the section larger, again, that's not buckling too. So that's why this would be very important concept. It's always about the length divided by the width, or in a way or another. We talk about the width in a minute, but keep in mind the behavior of the column. It's not just depending on the length of the column. It's not depending only on the width or the cross section of the column. It depends on the relationship between the two. Okay, we call it the slenderness ratio. We'll talk about it in a minute. It's always about the relationship between the smaller, look at this relationship, look at this one here. The smaller this ratio, the less chances for the beam for the column to buckle. Look at it, because the smaller, that means the shorter the length or the larger the width. That will make, how can I make this smaller?
Sorry, Aaron, you said the smaller the ratio?
Yeah, this ratio here between the two.
Is the less chance to buckling?
Yes.
Okay, cool, thank you.
So in other words, for this ratio to be smaller, that means the length will be smaller, L will be shorter, the length will be shorter, or B will be larger. So the smaller the length, the less chances for the column to buckle, the wider the base or the larger the cross section here, the less chances for this to buckle. Okay, so it's a relationship between two things. So based on this, as we agreed, we classified our columns into two main different columns, either short columns or long columns. And we have an area in between them, we call it intermediate columns, which is at this point, the column will fail in combination of the two failures between buckling and crushing or squashing at the same time. Okay, so the column first will try to buckle, but after it buckles a little bit, straight away we start squashing. This area here, we're not going to go too much into it. We will focus on these two so I understand the difference between the two. Now, the second question I need to ask you, discard that. Now, the second question I need to ask all of you guys, let's forget about this here. We'll go back to this ruler example. If for any reason, let's say I ask Saverio, can you please hold this ruler so it does buckle to the outside? So let's take this ruler to the side here. We'll be able to take it. So let's take this ruler to the outside. If, for example, I ask Saverio, can you please hold the ruler here in the center? Hold it here with something just from both sides so the ruler doesn't buckle to the outside. Initially here, let's assume in the first scenario, I managed to apply I managed to hold 5 kilograms before this starts buckling. If Saverio will hold it in the center, do you reckon that will hold more than 5 or less than 5 kilograms? So if I tell Saverio, can you please just hold it in the center? Don't allow this ruler to buckle to the outside. So if Saverio would do that properly, that means there's a chance I can load here 10 kilograms before this ruler will start buckling to the side. So let's put everything together now and try to understand what happens. For a column, guys, at the start here, the column can go to a maximum strength or maximum capacity. If this is a graph, this is here, a graph. The column can go to a maximum capacity here, which is the maximum capacity for that column is the yielding capacity, or let's call it NS, we usually call it next semester, okay? We call it the section yielding capacity for that column, which is here, in this case, is 10 kilograms. That's how much this can carry before we start crushing like this. But what happens before it gets to that, before I can carry 10 kilograms on that, somewhere here along the way will fail from buckling, call it NC, which is less, usually is less than NS. So the capacity of the column is less than the capacity of the cross section of that column, what we call it. And that is about NC equals to 5 in our example here. 5 kilograms, which is less than NS. Okay? So, what we're trying to do here, if for the future, what we're trying to understand, if you are designing a column, the first thing, guys, the first thing you have to worry about, how much will take that column to buckle? Because that's what will happen first. Look at it here. That's buckling here. That's the first thing will happen to the column. If you can manage that your column will not buckle, that means you gained a lot, an extra strength in your column, and you can achieve that higher yielding capacity. So the first thing you have to worry about when you design a column, what is the minimum load? Look at it. What is the minimum load? 5 kilograms will cause the column to buckle. If you get to know that, at least the minimum thing you can do, you can specify, for example, I'm your client, I'm asking you, what is the maximum load? Sorry, what is the minimum load this column will fail? You can tell me, Aaron, do not load on your columns more than 4 kilograms. Why did you say that? Because you calculated my buckling load is 5 kilograms and you applied your safety factor by 1 kilogram, which is about here 20%. And then you tell me your safe load is 4 kilograms. Okay? So this is roughly the concept. Does it make sense, guys, the concept? And please, it's time for questions, for discussion. What do you think of this concept? So what we took from this concept, if we apply an axial load on a column, the first thing we have to worry about, that column to buckle. If this doesn't happen, we could be lucky that we may reach that point, which is very theoretical point. There is lots of variables there, should be determined to be able to get to that point. It's a theoretical, not real life scenario. You hardly see column like this. Have you ever seen a column failing like that? It's very rare to see a column failing like that. Most of the time, we see the column failing in this fashion. We call it buckling. And your first job to understand or to determine what is the minimum buckling load on this column. That means what is the minimum load will cause the column to fail at buckling. If I can know that load, I can tell my client, well, this is your buckling load, and I'm buying a safety factor of wherever I choose. Then your safe load is this, which is always have to be less than your buckling load. So we call it buckling critical load. That's why we call it buckling critical load. And simply, this is the understanding of our topic. The formula for our buckling load is what we agreed on here. That's our Euler's equation that will determine our buckling load. There is very important concept before we get to that buckling load, what we call it the slenderness ratio. The slenderness ratio, if you noticed here from what we discussed, it's always about this relationship between the height and the cross section of a column. But rather than using B, just only the width of the column, because I'll give you an example. Sorry, I'll give you an example. We can't say if I tell you a column with circular cross section, oops, with a circular cross section like this, that will have the same width. That will have the same width as a square cross section. So B here is the same. But do you reckon these two columns, they have the same strength? They don't. Although they have the same height and they have the same width, but they don't have the same strength because the cross section between them is different. Okay? So rather than just taking the width only, and rather than taking just the cross section area only, we have the radius of gyration. The radius of gyration, K or R, sometimes we look into it, equals to I divided by A. The moment of inertia. So rather than saying for the slenderness ratio, to be more accurate, to account for these different cases, they have the same height, the same width, but different cross sections. And what about this case, for example? If exactly the same two columns, exactly the same cross section, but one of them is hollow, empty from the inside, like that. If I have these two cases here, both they have the same width, the same height, how can I make the difference between the two? That's why we're introducing a new concept there called radius of gyration. K, or sometimes we call it R. If you see R, the same. Radius of gyration equals to square root of I, moment of inertia, divided by A. We discussed the concept of radius of gyration before. I still remember, maybe with you guys, or you discuss it with Mike too. And if there's questions about this, please, let's take them away now. Yep, what's going on, Saverio?
In the second example, the hollow one,
Mm-hmm.
The area, we consider the area of the metal, right?
Yes, of course.
The part of the column that it's full of material.
Exactly. The particles will give us strength, not the air particles, correct?
Yes, okay, thanks.
Yeah, no worries. So let's go back to the concept of radius of gyration. We have to build up on this information, especially, and I guarantee, even for guys that have done engineering, I'm sure that most of you forgot them. We have to remember these different concepts. What is the concept of radius of gyration tells us usually just gives us good understanding. I still remember I discussed it with you guys. Just tells us good understanding where these particles of steel, they sit away from the centroid of a member. Are they very close to the center? Are they far away? Are they all distributed in all directions the same? Or in this case, for example, they are different. Like this here is larger, this here is smaller. So it talks about this formula by itself, by just working out this number, will give us a very accurate image of the cross section. That's why rather than using B in here, we're using R. And if I now put it all together, we got to a point we say, what will determine the slenderness of a column is mainly determined by what we call it the slenderness ratio. Which is equals to L, the length of the column, or H, divided by R. This is very important. If you get to R or K, please, if I say R or K, both are equally the same. It's just different abbreviation from different resources, okay? So think about it, look at this, from what we discussed, gives us a ratio between the length of the column and how the material is distributed in the cross section of the column. The minute you get this image, guys, you get much better idea about your column. The larger the slenderness ratio, so if this is large, let's say here large, that means your column is slender. That way, what will happen for the column? Straight away will buckle. Buckling. If this ratio is small, that means our column, we call it stocky. That means will crush. Can of Coke, example. Okay? Makes sense my drawing here?
Aaron, sorry, are we talking about the slender ratio or just about R in this case?
We're talking about slenderness ratio altogether.
Okay, so the smaller you mean will be stocky with all the ratio, the L over R?
Yes.
Yep.
All of this, if this is small, that means my column is stocky.
Yep.
Look at it. If this is small, that means the length is short, or the width is, or the radius of gyration is very high. That means we'll go back. When you think about short columns, straight away think of the can of Coke.
Mm-hmm.
That means the length is short and the radius of gyration is large for that length. If I have the opposite, which is I've got the whole slenderness ratio is large, always still think about the steel ruler example. This example here, the steel ruler that we had, okay?
Yep.
And that will cause just buckling straight away. We have a long and thin material. All right, guys? Now, in terms of that, now this is the new one. So are we clear up to here?
Yes, Aaron.
Okay, good. So what we got so far, let's go back. We talked about the length of the column, versus K, which is radius with duration. That will give us, that relationship will give us slenderness ratio. Of the column. From then, we will start talking about the buckling load. But before we go, that value of length, it's not the full length of the column. Because let me give you another example now. Let's get that exact ruler. What will be slightly different too. You just get rid of that. Without holding it from the side, just keep the ruler as is. Okay, let's take these two different rulers, which is they are exactly the same. And the same material, the same thickness, the same length. With one difference, the first one here, as is, I'll just push down. I'll put it on the table, here, just sit it on the table. This is the table here, just sitting here. And I'll push down from the top using my hand. We agreed, in theory, that should buckle like this. I'll just draw one side, okay, so to keep it just clear. That, in theory, should buckle something like that. Anyone disagree with that, guys? Is there anything not clear about this? What about if I tell you, I'll push down from here, but I'll ask Saverio this time to hold it with his hand here. Hold it. So he's holding it with his hand all around. Or what about this? Rather than that, I'll get the same ruler. So let's say this is altogether 1 meter long. I'll get exactly the same ruler, but I'll make it 1.2 meter. I'll purchase the same ruler, 1.2. I'll keep 1 meter standing out, but that 0.2 of a meter, I'll put it into concrete and I'll wait for it obviously to cure. So that's in concrete here. That is concrete. What do you reckon will happen there, guys? So I still have the same. If I look at the ruler here, this is the same, 1 meter outside here, that's 1 meter. The only difference between the two, this is just sitting on the table. This is cast into the concrete, sitting inside the concrete. So he's saying it still will buckle. Yep, perfect. That's 100%. So Fabio is saying, even if you do that, I still think this will buckle because still the slenderness ratio is very high. So the length to the width is large. I agree. But what other observations that you can tell me? Anyone else will have a different idea on this? Can I say that will buckle the same? Let me ask you this simplified question. Can I say this will buckle in the same as that one? What happened here? The first one can slide. Let's assume that it's not going to slide, Saverio. So Saverio, just to answer you, let's assume there's friction here, it's not going to slide. But Anna's saying, I don't think it will buckle the same, which is really good to start with, but it will buckle. Yes, for sure it will buckle, but it's not going to buckle the same shape. What would you suggest, Anna? What would be the difference?
Maybe it will be the size of the concrete.
The size of the concrete, yeah, okay, thanks for that. That's Hannah, I think. What about Anna? Anna, you said you don't think will buckle the same.
Yeah, I think the level or the ratio, I don't know how to say, but it will not buck too much. I don't know how to explain it, but I think it will be different, but no.
Okay.
No, as the first one.
You're saying that that distance there would be less. That buckling distance would be less. And that's, I think I got the same from Rafael saying the first one will buckle more. And Fabio is saying no, it will not buckle the same. Yep, that's it. That's correct for buckling. That shouldn't be a problem. Yeah. So, guys, let me tell you. Let me simplify it there for you. Do you agree with this? Let's say that. Let's delete that green light. What about if I tell you, and let's see if that will make sense. Rather than to buckle that way, what will happen? Because it's cast in the concrete here, it's forced. It doesn't have the option here. It has to stay straight because it's sitting in the concrete. All of that straight has to stay straight for a little bit and then start buckling from here. So we start straight. Look at it here. Because that's all kind of the same distance into the concrete, and then start buckling from this point here. Obviously, it's not going to happen like suddenly. We'll just do like this curving. Something like that. And then, yes, you're correct. That will cause for the buckling distance to be small. Smaller than what we had here. Whereas in this scenario here, the ruler could buckle from this point straight away. It didn't wait up to here to start buckling. Straight away buckled from here. Does that make sense? Guys, anyone disagree with that? All good?
Sorry, Aaron, the red part in the left-hand side drawing, is that red part there is in the concrete?
That's the part that's sitting in the concrete.
Okay, and the other side is not in the concrete, right?
Yeah, this here, the 1 meter outside of concrete. So I'm saying, for example, for the first, let's say 100 millimeters outside the concrete, which is 10%, assuming, which is in theory should be about 15%. So that will be 150 millimeters outside the concrete. Will stay straight, and then we'll start buckling again. Does that make sense?
Yeah,
perfect.
Totally.
Okay.
Yeah, thank you.
And obviously, guys, you would agree if I will have exactly the same thing from the bottom at the top. So if I make the top sitting in concrete too, that will make it do the same. So let's assume there's a third case here. That's it. Let's go to here. No, it's refusing. There we go. Let's assume there's a third case here, but I'll make this ruler at the top sitting in concrete. All of that is concrete. And the bottom is sitting in concrete too. And obviously the distance between the concrete is still the same. 1 meter, sorry. That's the clear distance, 1 meter. So this time I'll make the ruler 1.4, 200 millimeters sitting in this concrete, 200 millimeter that concrete, and between them there's 1 meter. So the buckling shape or the deformation shape will be this time straight, then start buckling from here, then goes straight, then goes back. Okay, so again, that will buckle less than the two other cases. So there will be very small buckling here in theory. More accurately, that will be very small buckling. All right, guys, make sense? This is, guys, what we call it the effective length. So what we talked about here, the 3 examples that we looked at, 3 of them, in theory, they are 1 meter ruler or 1 meter column. So let's forget about rulers now. Let's grow up a bit rather than rulers. Let's talk about columns. If I have 3 different columns, the 3 columns, they have the same length, but they have different fixing on the 2 ends. That will determine what we call it, the effective length. So for this column here, let me write them down underneath the columns. For this example here, guys, what we said, L equals 1 meter, but LE is exactly the same, nothing changed, 1 meter. Whereas in this example, L 1 meter, that's the actual length, but the effective length for that column, LE, is shorter. Look at it, that's where it start buckling from here to there. We call it 0.85 times L, which is times 1 meter, and that would be 850 millimeters for this scenario. For the third scenario, L again equals to 1 meter, but this LE equals to 0.7 times L equals to 0.7 times 1, and that would be 750 millimeters. So let's have a quick look at your comments to start with. Before I look at your comments, doesn't make sense, guys? Look at it. The length and the effective length for this column, because I have pin. Let's rename these supports. That's pin, support. I'm not restraining the column, and that's pin. I have here fixed pin. In this example, I have fixed and fixed. All good? Doesn't make sense, guys, the 3 different cases we got there. How
700 millimeters in the last one, not
sorry,
750.
Can you say it again, please? Sorry. Oh, yeah, 700. Yes, sorry. Thank you, Stella. Sorry, guys. Just thinking of too many things while I'm writing. So, guys, do we understand the difference between the 3 different cases? And does it make sense? So the fixing always affects the length of the beam. So when we're talking about here slenderness ratio, when we talk about length, relationship with radius of gyration, or what we agreed on, the length comparing to the width of the column, the length, it's not as simple as just the actual length. It's about the length and how is this column fixed to the surrounding structure. In this case here, I've got, look at this column. At this part here, it's forced to stay straight and then start buckling here. If this wasn't fixed into the concrete, that would start from this point here, just rotating straight away to the outside. But it's forced to stay straight a little bit and then start buckling to the side. So, before I read your comments, guys, let me just, again, based on this, let me simplify it for you. I can draw the first column. What we simplify it is like this: pin, pin. And LE equals to L, we say in this case. The second case, I can say fixed pin and LE equals to 0.85 of L. And in this case, fixed, we say LE equals to 0.7 of L. Does it make sense now, these diagrams?
Aaron, I just didn't understand why did you use 150?
Okay, that's why.
Example.
Because look at it here. LE is 0.85 of L. That's the rule for it, the formula. So 0.85 of 1 meter is 850. That will leave 150 straight. I'll discuss that.
Yep.
I'll discuss that later on, so you don't have to concern too much about this, okay? But let's
Thank you.
in terms of the cases, guys, does it make sense what happens for a column? So when we push down on that column, if that column was pin, think about it. You're carrying a ruler with your hands and you're just pushing down on it without restraining that ruler. The whole ruler will buckle away. Look, actually, that's a good thing. I can draw that shape for you. The buckling shape for this case is just like this, all together. Whereas the buckling shape for this case, it's forced to stay like this, and just 85% of it, look at it, 85% will buckle. The 15% here will stay straight. In this case, exactly the same, 15% from the top, 15% from the bottom will stay the same, and we'll leave 70% only between them will buckle. See, large buckling, smaller buckling, slightly smaller. Let's make it slightly, slightly smaller buckling, and the smallest buckling between them all. All good? So I've got Fab here, you've got some comments there. You have another problem with the situation because you are creating non-normal force at point where stop buckling. Yes, that's something later on we talk about it called magnified moments. That's something completely different. We will talk about it later on because Fabio, because anyway, we are trying to avoid this anyway. We don't want to get to that point and getting to a point that we have to deal with it. We are trying to stay before we get to buckling. Do you guys remember what we're trying to do? When we talk to our client here, we're talking about I'm choosing a load that I don't even get at all to buckling. So what we do, we calculate the buckling load, and anything below the buckling load will be the safe load. That's what our job is. All right, guys, so I've got how much does it gonna buckle? That's depending on the material, Rafael. So Rafael is asking how much does it buckle to the outside? That will depend on the section shape, the material, the strength of the material. There are lots of factors into it. But as we agreeing, guys, look, remember, please, this is already, when you get to the buckling, please, buckling is failure. We shouldn't get to buckling. Buckling is a sudden failure. So we shouldn't get to a point that our member is buckling. All what we're trying to do, we are calculating where buckling will happen. We are calculating where would it happen, the buckling, and stay away from it, stay below that. So if we understand where the buckling is happening and we stay below the buckling load, that means we are safe. So it doesn't matter how much you will buckle, doesn't matter all of that, because hopefully you don't get there. By the time you get to that, trust me, you won't have time to stand there and measure it. You'll be running away. Okay, that's for the first part for lecture, guys. Let's have a break. And after we come back, we'll put all of this together in formulas. Now we got the understanding. We'll put it into formulas. You'll find them very easy. And then we start taking some examples on that. Okay? Any questions before we go to break? All good? All right, good. All right, guys. I will see you after the break. So it's about, yeah, Severio has something about what? Buckling, compression, shear, and America. Exactly. Most common type of structural failure.
No offense to anyone, of course.
No, don't worry. None taken. I'm sure the Americans, they agree with you. They're not very happy with what's going on.
I was actually Googling difference between bending and buckling, and I just found that picture.
Yeah, fair enough. No, it's all good, mate. All right, guys. So let's have a break. So it's 12:30, assuming now. Let's all be back by 1 o'clock, please, so we can start looking into the examples, okay? All right, guys. I will see you after the break.